Good afternoon, everybody. Welcome to another video where I'll explain how to implement a certain data structure in C. And today we're going to have a look at binary trees. We've covered some other data types already. First of all, we looked at hashes some time ago, where we discovered that having a hash is really good if you have a specific set of elements only, because it will be able to map directly from your hash key directly to a single item to find, right? That's been a good way of finding data quickly. And then in the last video, we had a look at sets where if you had a specific number only, we could quickly find out with only a single operation whether a data element was present or not. And both of these operations are all O.O1 operations, all pretty quick. But there are some issues, right? I mean, if you looked at a hash, and in the case where you, for example, only had 10 buckets, like I did in one of the videos, but you end up having 20,000 elements, then these 20,000 elements are going to have to be spread out over those 10 buckets, meaning that specific bucket could potentially have up to 20,000, but on average about 2,000 elements. And at that time, it is no longer a simple ON operation mapping a hash key to specific elements, but you ended up having to search through whole lists anyway, and that isn't, of course, very good. Now, the data type that we're looking at today is a binary tree. And a binary tree basically is a clever way of making sure that any data that you find for your key takes the least amount of possible things to find. Now, just let's illustrate a little bit what we're doing here. It's like the data that I'm going to use is I'm linking a specific number to its English spelling. I mean, it's not the most useful data set, but at least it will teach you a little bit on how those binary trees work. Now, let's switch to my drawing first, and we'll start with what do we need to store for each node? Well, for a binary tree, what you need to store is the key. In this case, it's our number. What data we want to store? In previous videos, what we've done is we created like this abstract data type. You might remember the elephants as the data to store in the tree, but I'm going to want to keep it a little bit simpler here. So the only thing that we're going to store is a single string element. And then you need to remember the left and the right. And what left and right mean in a moment, I will show you how that works. But first, let's start drawing our root node. And for example, the root node, making sure on the screen here, what we have here is we have the root node. And well, what is the number that we're going to store here? Well, I prepared a list earlier, and let's just follow this through and see what happens. So the first number that my shuffled list of all the numbers from 1 to 100 it was 24. So our key is 24, and then in English that is spelled 24. So this is our root node, the first element that we're adding to our list. And then there's two other sides here, which is your left and your right node. Now, the way how this works is that every time you insert something in a binary tree, you see whether the number that you're inserting is larger or higher than the number that you're currently looking at. So if you can see in our list, the next number that we're looking at is 14. So our left side is going to store the number 14 because 14 is less than 24, right? So we will store 14 here. And then we set our pointer up that way. What is the next number that we're having? Well, it's 10. So let's follow that. Well, 10 is less than 24, so we go to the left, but this is already set, right? There's already an element here. So we can't just create our new element and store it there. Instead, we need to follow it here. Now, 10, of course, is less than 14 again, so we create our new structure here. It says 10. And we set up our pointer again. Now the next element in our list is 29. So if we look at this, well, 29 is larger than 24. And because this one is still empty, we're creating one that says 29 here. What's the following is 54. Oh, sorry, draw a pointer in here. Let's move this a little bit over. It's 54. Put our left and our right. And then what is the next number is 12. Well, 12 is less than 24. It's less than 14. So we end up at 10, but it is larger than 10. So we then draw it here. Oop, falling off the screen here. Drawing the 12 here, and so on and so on. And that is pretty much how you build up a binary tree. By drawing it out on a sheet of paper. But of course, what we want to do is we don't want to draw it in a piece of paper. What we want to do is we want to actually implement this in C. So the next thing we're going to look at is to see how we can implement that. So we need to remember that every node in the tree has a number associated with it. And then it has the text. And then we have our left and our right pointer, which are pointers to nodes again. Okay, so let's have a look at the implementation then. Oh, make sure I'm on the right screen here. Now, I've already prepared a few things in here. Things that we have looked at, so you've already seen our numbers list. There's also a one where it's just all the numbers in order. And I have already picked up my read file, C file, from that I basically copied from a previous file, but slightly modified. For doing some things, but we'll have to end up modifying that. But the first thing that we want to have a look at is what do we want to store in our tree, right? So let's open up our tree.h file and see what we need to store here. Well, this is an H file, so in every H file, always remember that you put in a guard. And this is a common thing to do. And well, what do we need to store here? Well, what we need to store is our tree node structure. We call it tree node, or we can call it node. Doesn't particularly matter. Let's call it tree node for now. And what we want to store is, well, we want to store our number. We want to store our data, which in this case is the English spelling. So I'll just call it English for now. And then we have a left pointer, which is a pointer to a struct tree node, which we call left, and a struct tree node that points to right. And then I shall align those because that's what I like doing. That I always tend to use tabs for indentation, but spaces for alignment. Okay, so this is our tree node. Let's also create a main file where we will, well, I can already see coming that we're going to have to include stdio and I actually don't remember what the other one is. We'll see what it says up. I forgot what it is. But in any case, we need to make the main body of our script. As usual, we'll take argc and argv to basically set what our arguments are, and we make sure to return null in the normal case. That's basically our thing. Well, of course, we are going to have to include our tree node, and that's that. Now, we have to have a quick look at our make file, because at the moment there's some things in there that I've already set up, because I already have done tree.c and main.c. Tree.c is of course still empty because we haven't written it yet. But in order to make the make file work, we'll just create an empty file, and that's well, nearly empty, and that should then compile. So let me switch to where did I go? To this screen here. Type make. It says no rule to make target read numbers needed by test, because it is called a read file. Just rename it here. numbers, if you know how to spell. And yeah, I'm getting a few errors in there because read numbers we haven't implemented yet, and I'm going to have to do something with it. So for now, I'm going to have to remove that from the make file. So the make file is open here. Sorry, I'm getting lost here. We can always plop it in back later when we start doing something interesting with it. So make, never mind, clear, and we run make. And we get an error saying that tree node doesn't exist. That makes sense because we've called it tree. And now we're still getting an error because I forgot to add a semicolon at the end here. And now this compiles. Of course, when we run our program, it doesn't do anything because we haven't told it to do anything. Okay, so this is our simple tree node structure, and we don't really need to store any other metadata. It's just the tree node is good enough. So the idea now is that we need to create the tree, but we don't really need to create a tree. The only thing that you need to do is create a tree node, right? So we can set up our function that we need to create, which is tree node. I am going to shorten this to node because I am going otherwise a bit bonkers. It's shorted to type. That's never a good excuse to do something, but and we do that with our typical pattern where we call it CTOR for constructor, and then we have our number and our character that says English. Each node is going to have a destructor as well, which is just struct node, and these are things we need to implement. Well, we need to implement more than that, but these to start with. All right. So what do we need to do in the node CTOR? Well, pretty much the only thing we need to do is, well, we need to create a structure. And by definition, I always call them temp, and we need to allocate that by using malloc, and then we need to take the size of the struct node. And then we need to set the number to the number that we pass in. We need to set our English string, but instead of just assigning them, it's a very normal thing to do is to actually not just assign them, because that means that our node structure can't really do anything if somebody else frees up my string of data. So it is a very common thing to duplicate this or to do ref counting, but that we'll explain in some other new video. And then we need to set left and right both to null, which needs to be uppercase letters. And then we need to return that. So that is simple enough. Well, similarly, we need to do in the node destructor. We need to make sure that we free everything that we've allocated. So that is our string, our English string, and the node itself. So basically, the detour always does the exact opposite of what the CTOR does. But of course, we need to do other things as well, but we'll get back to that later. Now, creating and removing isn't a very interesting thing as well. What is an interesting thing to do is, of course, to add an element to our node, to our tree. So we'll create a function that says node add, and then you give that the tree itself, so the root of the tree, which is this tree structure, and then we'll give the node that we have just created. So that is another struct node, and that is an item. So that is basically the way of adding elements to it. Now, what do we need to do in adding elements? Well, copy this as well so that we can implement that. What do we need to do here? Well, first of all, if our tree is empty, then if the tree is empty, I mean, that means something is broken, and we need to return null. well, we can't return anything, but that's just a precondition. The question being asked on the channel is, I see that you use lowercase names for your structs, like tree_node instead of tree node and then a T and the end being uppercase. Do you have a link research to a page that you consider to be the reference in coding cell for C? I don't have one right now at the moment, but for most code that I have seen tends to use lowercase and the underscore or the kebab case, or if you want to call that. There are a few typical use cases where you would use uppercase letters for things like constants, but you don't really see the Stutley caps kind of style where you have things like tree node. It's not something you often see, although that of course depends on the programmers that of course do this, but I don't have a specific reference for this. I guess this is sort of ingrained for what I have. Okay, but let's get back to our adding the node elements. Okay, so if our tree is null, instead of returning, what we pretty much can do is we can set our tree to be null, or can set our tree to be our new item, and then we can return. The question, the point here though, is that this doesn't work. We don't have a tree, but if you set a pointer to the tree, you just end up setting the pointer in the local scope. You don't actually end up changing the thing that's being passed in. So this trick does not work. Now, how do you get around this? Well, we can either use a pointer, or we can pretty much get around this by just making sure that the first element that we actually add, we don't create node add, we just create a node before adding it. And in that case, we can make this a precondition of adding a leaf node to the node that we already have. Okay, now if our number that we have, that we're passing in, is how do you call that? If the number is smaller than the number that we're currently looking at, which is stored in tree number, then we need to add this to our left node, but only if the left node is empty. So if our left node is empty, if the one on the tree that is if it is not null, then we already know there's something on the left hand side. So pretty much what we then need to do is we need to basically walk down the tree, take the element of our left part, and then call node add on that. So for example, what you can do is you can do node add tree left, and then we do item. Basically, this is recursion. But it is kind of useless to do it like this because we don't really need to check for null here. Although, well, at the moment we will. I think there's a better way of doing this by using pointers, but that is too complicated for this video, so I'll skip that out. But I might actually do that if we have time in the next one or not. So, yeah, if the item number is less than the tree number, that's good. If our left node is not null, then we call node add. Otherwise, we can basically do tree left if is our new item. That's pretty good. And then once we've done that, we can return. Similarly, if our items number is larger than the number in the tree, and for this video, we're not going to concern ourselves with numbers being the same. But although we can potentially do that by just doing this comparison, but our numbers are unique, so we don't have to bother with it. And then of course we can do that for our left, and the same way as for the right side. And I'm just copying basically what I have here is item. And then we return, although that doesn't particularly do much. And that's basically adding our node. Now, yeah, let's actually have a look at doing something useful with that. So I'm going to bring back my read numbers file here, adding that back to the make file, because we do need to actually implement that. We need to read our list of numbers. Now, what do we need to do here? Well, I'm not going to go over this whole thing yet again. What I'd like to do is actually that, well, what do we need to pass in here? Well, we need to pass in our tree structure, right? And our tree structure, that is, of course, like this. And of course, that means we need to include 3. And anytime we find a number, what we want to do is, well, we don't care about the bounds checking here, because the numbers for binary tree doesn't matter, for set it did. But for every number that we have, is pretty much what we want to do is we want to do node add on our tree, and then, well, we need to add our data elements. So first we need to do is new node, which is our struct node. New node equals node ctor. We're passing on our number, which we have read from the previous file. We'll get back to the translations in a moment. And at the moment I'm just passing in the number string, which is the string that contains the number, including the number itself. So we'll fix that in a moment. If you remember what we have in the numbers, what we have in the numbers, let me get rid of these. We don't need this anymore. If you look at our numbers file, you remember that we have the number and the comma and then the string. A2i, the function that converts the numbers, the strings to numbers, which is what ATI does, should ignore the comma, and then we just handle that in a moment later in a different algorithm. But yeah, we create our new node and then we add it to our tree as our new node. And that's pretty much what we need to do for every element. Now, of course, I've already mentioned that we need to look at what the root is, or whether we have a root or not. I'm actually splitting this up so that it's a bit clearer to what we're actually doing and what we are defining here. I like having my things yeah, nicely organized. But yeah, this should pretty much do yeah, adding our elements. But we need to think about our main root node. Now, of course, what we do is we need to define that in our... get rid of this here. Of course, yeah, we create that here in our main file. We say it is null, and then we call our read numbers with the tree, but not quite the tree, because you remember that if we have our first element, we need to create the root. Now, there's a few tricks around this. We can just create an element that is simple null, which is a reasonable way of doing it. So I'll just do that now. We say just the number 0 and we say root as text. Let's just do that to start with. It isn't the nicest. Then we call our read numbers function, which basically will go over every element in our tree. Once it finds it, creates an element for it, and then adds it to the tree. Shall we see whether that compiles and runs? So let me usually doesn't in one go. See, I made a few mistakes as usual, but we have a friendly compiler that tells us what we've done wrong. So the first one here it says error unknown type name node in read numbers line 6. So that is line 6. That is because this is struct node, not just node. What else do we have? We do a malloc in tree.c, which we haven't defined, but our compiler says that we need to include stdlib. Oh. No. stdlib. I already alluded to us having to add that. What else do the errors say? It says something about std.dub, and that requires including stddev. In which file is this? Is in tree.c line 2. Yep. Let's see whether that was it. No. Still made some more mistakes. Let me clear this because there's more than I can see. Oh. Interesting. Something did work, but I thought I got errors. Oh yeah, we got some implements and declaration of function str.dub. And that pretty much means that, of course, that we haven't defined it yet. And if you get a warning like that, to find out where these functions are defined, you can use the man pages. This is in tree.c, and str.dub and variant says that we need to include string.h. So we'll do that. And that is in tree.c line 11. So just add it here. Now it is also a common thing to include the system defined, the ones with the pointy or angle brackets before the ones that we have written ourselves. And we're still getting one warning here, and it says implicit declaration of function read numbers. So read numbers, although we have defined that in this file here, we haven't created a header file for this because we simply haven't done that yet. Now, there's a few ways of doing that where we can create a header file where we define a read numbers function, or we can cheat and basically just say that we have this function. And you do that by defining extern. And that basically says to the compiler, we have this function. It isn't in any header file, but we provide its definition here so that you can compile it and type against this correctly. Now, it's not a nice way. I think it'd be much nicer if we do a read numbers header file, but because we don't really want to, or I don't want to bother with it, and I wanted to show externs, should work like this as well. So we run make, we get no warnings or errors. So what happens if we run this? Nothing, because at the moment, of course, we only put our structures in. But let's have a look at what actually ends up happening in some of our functions. So I will set a breakpoint in main.c, and I want to set it after read numbers has been called. So that is line 13. So let's run this. And then we can show what is in our tree. So our struct tree is our root node, and what is in there? Well, it has null, has English roots, and then on the left side we have nothing. That makes sense because all of our numbers were smaller or were larger than 0. So we find everything on the right hand side of our tree. So what is in the right hand side of our tree is the number 24, the text 24, 24, and then we have a left and a right. Now we can continue with this to see what's in here. So what's on the left side is the number 14. And what is on the left side of that? We see the number 10. If you remember, that is exactly what our image shows, right? Our first element here, the 24, on our left side we have the 14, and then again on the left side we have the 10. But 14, as you can see in the screen, also has something to the right. So let's have a look at what it is to the right. We don't know that yet. And it says that is 19. That also makes sense, right? Now, if we look at the top one, 24, and we look at the left node there, right to get to 24, and then right again, we sort of expect there to be 29. And exactly we have 29 there. Let's see whether we can get to the end here. We get 54 to the right. One further, we get 73. And then we get 74. 76. 97. And 100. And 100, we have nothing further to the right because this is the highest number. How many steps did we need for this? Well, we started with 24. That was the top node, so that is 1. And that gives us this one here. So 24 is the first one. Then we had 19 because the 10 was to the left. So this is 1. Sorry. 14 is the second one. 3, 4, 5, 6, 7, 8, 9, 10 steps. So in 10 steps we managed to find 100. Which is pretty good, isn't it? So there's 20, or what did I say, 10 steps to 100. But if you look at it, what would be the optimal way of, what would be the optimal number of elements to get to 100? What is the best way of, or the best way of finding our numbers is always going to be if the numbers are spread out in such a way that every time you add a node, it always fits specifically in either a left or a right side, in such a way that the tree is balanced. Now let me see if I can show you what that with only a certain amount of numbers. Okay, so let me use the other side of my page here. And then let's see whether we can draw the numbers. So let's do this just for 16 numbers, right? So we have the numbers 1 to 16. So the first number that comes up is the number 8. The number 8. And then the next number that comes in is the number 4. Then the next number that comes in is the number 2. Then the next number that comes in is number 1. They're all smaller, so they will all be on the left-hand side. Now, what if the number 3 comes in? Well, it is smaller than 8, it's smaller than 4, but it's larger than 2, so we do the number 3. Now, let's do the number 6. Well, it's smaller than 8, it's larger than 4, so we draw the number 6 here. Then we get 5, and the number 7. Now let's now pretend the next number that comes in is the number, let's see if I do this right, the number 12. So we get the number 12 here. Then we get 14. If you follow this, we get the number 16 is oh sorry, I did this wrong. This should be 10. Because 10 is smaller than 12, but 14 of course is not. And here we get 14. Because we only had the numbers 1 to 15, not 16. Doing 9 is still larger than 8, smaller than 12, smaller than 10. And then 11 shows up here. We get 13 here and 15 here. So now to get to any number, how many steps do we need? Well, we need to do 1 step, 2 steps, and 3 steps to get to any leaves. So if you calculate actually what this is, the number of steps is always going to be the best number that fits in this power. So you get in a 2 log n, and n being the number of elements. And this is the best possible case for finding every number. In 3 steps, or rather in 4 if you count the 8 itself, in 4 steps you can find any specific numbers. And if you calculate 2 log n of 16, you end up being 3. Or sorry, 4. because if you do 2 to the 4th, and so being 16 again, right? So with 4 steps, you can get to all the numbers from 1 to 15. I must have made a mistake somewhere. No, it doesn't look like it. So, and this is the best possible case how you can get this number. What is the worst possible case? What is the worst possible case for finding the numbers? Well, let's do this a bit smaller and we only pick the numbers, say 1 to 6. So first we get the number 1. Well, the number 1 starts here. We get the number 2, a second one, then 3, then 4, then 5, and then 6. And that is the worst possible case, right? To get to the number now, you need the maximum case of steps that you need is 6, which is also the amount of elements that we have. And that is the worst case of this algorithm. So in the best case, it is the 2 log n, and that of 6, 2 log n of 6 it's larger than 2, but smaller than 3, I think. So the best number of steps that you can to get to all the numbers is going to be 3, but the worst one is going to be 6. So there's this wide range of numbers that you have here that made this harder or easier. Okay. To get back to our example is that there's a few things that I want to change still. First of all, we haven't implemented our search function yet. So let's implement our search function first. But before I want to do that, I want to get rid of the number here and the /n at the end, because we are not interested in this number. And yeah, so let's do that. And hello, Pink Emma on the stream. So let's modify our read numbers and see what we can do there. So yes, we already had our a line here to read from the file, but the string number that we want to put in is not something that, well, we don't want to /n at the end, and also we want to make sure that it skips the comma, and there's actually a way of doing that. So we can set up a character pointer. This is annoying. When we set just a text, and the text starts at a function that we can call strcr. We search in our number string, and we search for the comma. And what this function does is, like, I need to confirm this with our man page. Because I can, just like in PHP, I can never remember the order of arguments. It says locate character in the string, and it says strcr. It wants the string first, sorry, the character first. No, I got it right. The string first and then the character second. So we had the string first and then the character, not the string, and then see, these are two different things. Small and big, single quotes and double quotes. And then here what we can do is we can do the text. We do make. Let's hope I didn't make any mistakes. I did. It says that we forgot to include string.h. And if you know what I can do about the spammers, I am more than welcome. You are more than welcome to let me know, because I don't know how to do that. Can I block people? Oh, it's already blocked. Okay, so I can't block it again. Okay, yeah, so now doing the comma, let's make should work. We run our program again in GDB. We set our breakpoint on, what was it, line 13. Yeah, that should be the right one. And let's see what's in here now again. So we do show the 3. We show the first right element. And it now says, instead of saying the lovely 24, it says comma 24. So that's not what we want, right? We want the next character in there, so we need to skip the comma as well. But it is important to actually check whether it actually found the comma in the first place, otherwise we can do bad things. So in this case, we actually need to check the return value, like you do with everything. And if it is null, we simply skip over the line. Otherwise, we just add 1 to the pointer that we found. And because this is a character pointer, you can actually do arithmetic with pointers. And basically, if you do +1 on a pointer, it will, in memory, go to the next memory element from the original pointer, taking into account the size of what we're storing. And because we're storing characters, we have defined a character pointer. It skips 1 byte in memory because a character takes up 1 byte. If it had defined this as an integer pointer, it would have skipped 4 or 8 bytes, depending on your 64 or 32-bit machine, even by doing just +1, because it means adding 1 element, not 1 byte here. So let's run this again. Handily, you can type make from within GDB. We run this again, and we do our print 3 write. And then it says can't access memory at address null. Because I did something really silly, instead of doing making sure it was full, I checked whether it was empty to skip out. So try this again. Run, yes, run from the beginning. Do the printed 3, and then let's see what we get in write. And then we get our 24, but we still have our annoying /n at the end. So we also need to reset that. So how do you do that? Well, you can do that by first checking what the last character is. So you can do a text index, taking the length of the string, and if that position is a new line, we set that position to the null character. Like in C, the end limiter of a string is a null character, but it doesn't particularly care that we're just overwriting that bit in memory. It doesn't particularly matter. When the string gets freed, which we haven't implemented yet, then whether there's a null or not, it doesn't matter. The memory manager knows what the original length of the string was, so doing this should be fine. Now, let's compile this again. I messed up because text is not a function. It is a string, and we can we do need to do this correctly. Yeah. The brackets need to be on the right place. It compiles. Let's run it. We do our print of the 3 write, and then it still gets 24. Well, why is that? Because the string length starts counting at 0, meaning that if we do this length of the string, it's never going to be n, it's always going to be the /0. So we need to do the -1 to get 1 position back from the /0 at the end of the string to get to our new one. So let's run this again. And we print write, and then we get, as we would expect, the number 24. So that's good. So we have implemented that bit now. Now, the next thing that I want to look at is we want to give our program a number again, like we did in previous things, and show what the English spelling is for this number. So we don't read numbers anymore. But I am going to steal something from our previous program where we read an argument from the command line. And I see that this is an array of pointers. And we're just basically copying and pasting this bit. So we're making sure that we pass in the right amount of arguments here. The number string and the number that we're looking for. Of course, this is no longer a Fibonacci number, but it's just a number. we do convert it from a string to a number like previously. Of course, it's now number. And then what we need to implement is well, finding out what our data is. So the return value that we get from finding something is our new number. I'm just going to overload number string here to see if that works. So we do node find. We do the number that we're passing in. If we have a number, if it has found our string in our tree, then we will do printf. We do say in English is, and then we add the number that we put in, which was our number and our number string. And if we didn't find it, we say don't know what in English is. And we pass in our number again. And there we go. Nope. And add our brace. Now, of course, we do need to implement our node find operation. So that is the next thing to do. We open our tree header file. We do void node find. We start with our node, our tree, and then the number that we're looking for, and this then returns our English spelling translation, hopefully. So we do node find. We add that now as an implementation as well, of course. Now, how would we go about, sorry, that is in the wrong file. It needs to go into the tree file, of course. Node add node find. Now, how would we go about finding this? Well, I don't really want to write a recursive function here. I want to implement it in like a loop structure, just to show you a different way of doing that. The problem with sometimes with recursive structures like that we used by adding nodes is that if you have a lot of data, you get lots of nested levels of functions calling other functions, and that can return in a Stack Overflow. Again, at some point I can probably explain better what that means. So in cases where you don't necessarily know how many elements you have, it is sometimes much better to write algorithms not in a recursive way, but doing that in a loop structure, and that's what I want to do for finding the node. We set our pointer. The pointer, that is the thing that is going to loop over our elements, and initialize that to the root of our tree. I realized that this is now slightly falling off the screen. That's the main. Although we don't care about, at least it's now no longer next to my face. Okay, so what do? We do a while loop until we have found our number. So until pointer number equals our number, or we find that our pointer is empty. It has found an empty branch. And then if the pointer is found, we return the element that it currently points at, which is English. Or rather, what we should do, because we don't want the calling function to have to deal with memory management, we should actually duplicate this, and then the calling function, the one that calls node find, is responsible for the data that has been found. Again, this doesn't necessarily have to be the way how you do that, but because we're only dealing with a single string, it is probably the best way. At some point I will expand that to doing reference counting. If we can't find it, we return null. Okay, now Actually, I'm going to switch around my loop, and whether that's a good thing or not, we'll see in a moment. Okay, so as long as our pointer number is the number, and now we need to swap that around. So if our pointer number isn't the number and we still have a valid pointer, we can do more things. So this will break out of the loop if the number that we're pointing in is correct, otherwise it isn't. Now, what we can do now, if our number that we're looking for is smaller than the current node element is, we can say pointer equals pointer left. Well, if that is set, that is fine. And then we go into the loop again. That is no problems with that. If the number is larger than our current element, we look at the right-hand side. So we set our pointer to the right-hand side. And then the loop, if it sees that our number matches, will jump out of it. Or if it is not valid, will also jump out of it. So that should be our node finding implementation. Now, we've already implemented that here, but as I said, if we find a number, we should also free it to be correct. To be on the good side here. And that should be our implementation. Let's see what we do when we type make. Oh, I'm getting a few errors in here. I forgot to include some header files again, so exit is missing, which requires stdlib. So let's add that to our main file. Is that all? Let's do this again. It says node find number is incorrect in line 24 because we forgot to pass in our tree. It wants two arguments, the tree and a number. We only pass in our number. And now it compiles. Excellent. So now let's run our program and see what it says. So if we run it with, say 7, and it finds 7 in English is 7. Now what happens if we do 19? It says it's 19. What happens if we do 199? Oh, that's not good. We're getting a segmentation fault. So let's try to find out why that happened. So let's start GDB. And I'm doing something. It says ptrace operation not permitted because and now Firefox crashes. I'll deal with that later. Yes, so GDB, if it is just the program, you can just type the name of the binary, but if there's other things, it wants args in front, which is kind of annoying, but so it goes. Okay, so let's run this from the start and see what it says. It says it finds a segmentation fault. So let's create a backtrace, and it just happens in here. Okay, that's fine. So what is our pointer? Our pointer is null. Okay, that makes sense now, right? Because what we're doing here is like, we're doing, well, pointer to number is a number, but if you do initialize something from, or try to read something from null, which is what pointer is, we can't read that. So what we should have done is always check whether you can read from the top level elements first. And in this case, that is of course pointer. So instead of doing that at the end, we need to do that at the start. Okay, let's do make and then run again. And then we still get a segmentation error. What is it this time? So we do BT. Oh, that's not good. I have no idea what it means. So that's, sometimes it gets a bit wonky and it wants you to restart from the start. But we still get the segmentation fault. We get it in printf. And it says here, don't know what %s is in English. %s is something that you use for strings. But that's not what we passed in here, right? So if you go to frame 3, our main, so it wants the s as a string, but we passed in a number. You can't do that. But basically that means it's trying to read this pointer the number that we're looking for, 199, as a memory address. And I think if we use valgrind to show that, it will actually tell you that it tries to read from address 199. So what does it say here? It says invalid read of size 1 in STLang, and it says address C7. Now, how much is C7? We can do, if you remember how much is C. So C is the 12th character, because 9 is 9, A is 10, B is 11, and C is 12. So that is hexadecimal 16. And then what is 7 is 7, and I'm sure this is going to be 199. So it will tell me that I'm trying to read from memory address 199. Of course, that is not what we want to do. What we want to do is show the number instead. So let's make this again, run our number. We still got memory losses. That's fine, because we haven't done anything with memory yet. But when we run this, it now tells us correctly what 199 is in English. But it's kind of interesting to see what how much each step actually takes. So what I'd like to do is I want to actually count the amount of steps that are needed. So if I do steps is 0, and we do every time we end up in this loop, we do steps plus 1, and at the end, if we find it, we do printf of steps, just to see how many steps each number takes. I bet I forgot to include, no, I should have all the header files. We'll make, printf, I miss stdio, so let's add that. Make again. Let's run this with 199. Well, it doesn't know what it is, so it doesn't show that. What about 100? It took 8 steps to get to 100. What about 99? 10 steps even. And by doing this, you can actually sort of calculate the average. If we really want to do this, I can't be bothered, but it actually shows you a little bit how much this is. Now, do you remember what the top root node was? Let's see what my sheet said. I think it was 24, right? So if I do it with 24, you'll get 1 step back. And there we go. So we've implemented adding our elements and freeing it. But what we haven't done yet is freeing the tree itself. So that is the last thing that I would like to implement in this session. And then in some other future video, we'll actually look at how to improve on the worst cases. Like, if you remember, I had here with the number 6, right? 6 elements needed 6 steps, and we don't like that. So we'll have a look at how we can improve on that with some better trees, for example. But yeah, the best thing to do, the last thing to do, is actually freeing the structure, or freeing the whole tree. And to do that, we already have implemented the basic of freeing the node itself and its the data that it stores, but we haven't freed up anything else. So I'm just going to add it to our main program node detour of our tree, which starts with root. But we need to do other things in here as well, right? I mean, if we have a left element, we need to free our left element. And if we have a right element, we need to free our right element. And instead of doing a loop, I'm doing this in a recursive way, because that is currently the easiest implementation. And that's pretty much it, I think. Let's see whether my hypothesis actually works. I type make, that worked fine. Let's run it with 24. I get no errors. Let's see what valgrind says. It says all heap blocks were freed, no leaks are possible, so I would call that success. So with that, we have successfully implemented a binary tree, a very basic binary tree that doesn't do any rebalancing to get away from the worst case states, as we saw with the 6 numbers, all in increasing order. And we have implemented a finding way of doing things as well. Now, there are many things that we can improve here, like at the moment we had to create this arbitrary root node structure, which isn't very nice, but it does, it does work. But it introduced an extra step that you might not necessarily need. In order to get around that, we need to use pointer-pointers, and I think for a basic introduction to data structures in C, that is not the way to go. So thank you very much for attending again, and I will be back next week.